What we have today is a presentation on Vega and other in-silico tools developed by Istituto di Ricerche Famacologiche Mario Negri, and I will
just to refresh a little bit your memory. So this is the home. At the center, you see we have a center of all the machinery. We have a so-called, what we call the Vega in-silico models. And then we also have tools for read across. So we have the Vera models for read across, the ToxRead, and we also combine the evaluation done through read across with the prediction, and this is done within the Swan software. Since we have a large collection of models, it is also possible to somehow integrate the different models, for instance, for prioritization. This is what is done within Janos. And if another possibility is to integrate the models for read across. This is what is done in the model that we call Vermeer. And once you have information regarding, let's say, the risky chemicals, you can also aim to substitute the risky substances, so to move toward candidates, a safer alternative, greener substances. This is done by the software that we call ToxRaser. Here, this is the home, and below you have this link for the community, and from here there are a number of projects. I mentioned this because this is a kind of a shortcut to the concept project, and I will mention this later on. Indeed, Vega, the software, has been developed not only by Mario Negri, but different groups also outside, also model from other platforms, and we acknowledge the contribution funding for many projects. This is in the past, and later on during the presentation we will see the new projects that are still supporting. And from the concert project available from that link, from there you can get access to other pieces of information that I will mention. So using Vega...
Sorry to interrupt, Emilio, can you hide the bar in the bottom if you click on Nascondi? Thank you.
Yeah, I'm sorry, yeah. So the use of Vega is quite simple because you can simply introduce one single structure using SMILES, or if you have a series of 1,000 chemicals, important then. And then you can select the models because maybe you are interested only in ecotox or human tox, and you can select one or all the models of interest for you. And then you have to decide if you want or a table, if you have many 100 substances, or the PDF to provide the report, and you can choose one report per model, one per substance, or organize it in different ways. Whenever you have a prediction, whenever you use a Vega model, beyond the prediction, there's another software that is working, and it somehow evaluates if a prediction is, if there are issues. And this tool is a tool that is associated to the applicability domain. And in particular, it measures in a quantitative way what we call applicability domain index, DI. And this value is composed of a software to get this quantitative value, which goes from 1, which is very, very good, to 0. It is composed by a number of checks which are automatically calculated and done by the software, so that if you have issues, that this is indicated. The advantage of this tool is that this is offered by all the models. It is based on different checks run automatically by the software. It is independent on the prediction. It is quantitative and transparent because it indicates if there are issues related to maybe there are not similar chemicals, not so similar, so on. And in this way, you can compare the different models. So let's imagine that you have two models, model A and model B, with different applicability domain index value. And so you can prefer to use the most reliable, or you can use this value as a weight to somehow combine the results of different models. And with other colleagues also from EFSA, CCS, we have used this kind of concept on the integration of results, both for in-silico model and read-across. And this is the link of this paper is freely available in open literature. Beyond this, let's say, overall assessment, there's a summary, indication of reliability, or maybe issues of interest, the presence of structural error, whatever, and you can visualize the 6 most similar compounds with their predicted and experimental value, and depending on the mode, if there are structural errors, they are also indicated and if structural errors are in agreement or not between the target compound and the similar compound. Another software that I mentioned is for read across is ToxRaser. This is even easier to be used because you simply need the smart. You have to choose how many chemicals, similar chemical, 3, 20, whatever, and then point. And there are read across modules, tools for tens of different properties. And ToxRaser, let's say, put in a table, of course, with the similar compounds. For instance, here, at the center, you have a target compound, and then the 3, 4, 20 most similar compounds. But in addition, you have indication or representation of elements, let's say, for instance, depending on the endpoint, for instance, structural errors, which are associated to adverse effect or which statistically are associated to lack of effect. So these are represented here by these triangles. And if you click on the triangles, there's an explanation what kind of fragment it is. If you click on the circle represents the similar compounds. There's the case number, the structure, and so on. And there are many of these rules elements for reasoning, for instance, for mutagenicity aims. We have more than 800 of these rules. Some are associated to toxicity, other are exception rules applicable to this kind of structure. There are other rules which are not necessarily specific to one or the other fragment, but in general decrease in toxicity, so it can be related to the polarity and so on. And also information in this way related to neutral fragment, which may be useful when you want to explore similar chemicals and maybe you have unknown moieties or what may be the role of this moiety. Does it mean something associated to the effect? And in ToxRaser, if endpoint is continuous, there is also the possibility to have graphs. And so again, you can choose a 6, 15, whatever, similar compounds, and you have a plot. For instance, this I think is BCF, yes, versus log P. And then there's vindication of the substances, and you can make a reasoning to try to see if they are indeed similar or not, or if there are some unusual moieties. I mentioned Vermeer. So now we have seen the individual models, but in the case of risk assessment, there's a possibility to combine different models for risk assessment. Let's see, for instance, the tool for cosmetic that we call Vermeer Cosmo Life. In this case, we have a clear reference to the notice of guidance of SCCS, which is the Scientific Committee of Consumer Safety. And indeed, the steps are the hazard identification. If we have experimental value, they are provided because there's also a database of values. If not, the software uses the Vega model for the endpoints of interest. Here we're speaking about cosmetics. And then another level of software related to the exposure, both external exposure and internal exposure. In this case, we are considering the skin permeation, so there are the models which can be used to evaluate this. And then at this point, the software compares the value for the toxicity and the exposure. using the NOEL. We were also introducing NOELs specific for organ-specific values. And at this point, you can characterize the risk. So this is how it works with the software. We're speaking about cosmetic products, so not only ingredients. Usually in a product, you have many ingredients, so you have to specify, okay, I'm interested in this kind of product with ingredient 1, 2, 3. And we are speaking about the concentration. So you have to introduce what is the amount of a certain substance, because this it's relevant for the risk assessment, the concentration, the exposure. And so you can use the smiles or other tool to introduce the chemical. And then we're speaking about the cosmetic products. So you have to specify if the product is a shampoo or a cream or whatever. And this is related to the exposure scenario, the frequency of the use, and all these pieces of information are taken from the notes of guidance, because for each cosmetic product, there are specific, let's say, frequency of application, the surface of the body, and so on. And the information has to be also defined depending on the target population, if we speak about a newborn or different kind of person, because this again relates to the exposure scenario. And there are separate threshold values for this different kind of application. So the output, this is the summary of the output, and then if you click you can get the details. Simply reports, as we've seen, ingredient 1, 2, 3, and there are the information related to the annexes with the cosmetic regulation with the threshold values and blacklist and so on, that the software takes into account this. And if you have the issue related to hazard or issue related to the exposure, these are indicated, that the software calculates the margin of safety. And this can be useful only for trace amount of the TTC threshold of concern. Here you have information regarding I mentioned the threshold value. So if you have issues and you can, with a certain chemical, you can reduce the concentration. And this is one possibility to see if at a certain point, reducing the concentration, the risk is avoided, or you can decide to change the ingredient. And in this case, we're using another software, which is called ToxRaser. So ToxRaser is based on safety of substances. So there's a list of substances mainly related. In this case, we're speaking about cosmetics. So again, safe chemical, safe or chemical which have to be not used, blacklist, or chemicals with associated threshold values. So we have these three conditions, and there are lists taken from not only Europe actually, but also other countries, in order to be to have more pieces of information. So from the States, from Taiwan, and so on. But since we are speaking about the use, a candidate, a new chemical for a specific application, we also need information regarding the functional use. So I have to decide to indicate if the chemical is for skincare or preservative, if it is antibacterial or not. So a single ingredient in a cosmetic product may have a different functional uses, and so I have to specify them. As you can see, we are not only speaking in this case about the safety, but also the industrial application. And then another component of a software is the similarity, which is again done through the Vega similarity to something similar to what we've seen with ToxRaser. And the software also takes into account if there are structural alerts. So this is how to introduce this component. So you have to insert the ingredient, you have to select the use of a chemical of ingredient, if it is antioxidant or whatever, and there may be subcategories to better define the use of a substance. And then the similarity, you can play with the similarity threshold. If you can find something similar, quite similar, it's good. If not, you have to browse and search for something less similar in order to replace your ingredient. This was for cosmetic, and then there are other tools, of course, for other applications. For instance, in the case of food contact material, we're speaking about a completely different regulations. So there will be other blacklist and other threshold value and other endpoints. We are not so much interested in skin sensitization, but maybe in the oral exposure, something more important. But for food content material, the software also takes into account the migration from the container into the food. And so it calculates also this kind of, let's say, behavior if bisphenol A or whatever or other contaminants may migrate depending on the temperature, on the duration of the phenomenon, and so on. I mentioned this project previously, Concept Reach, here because Vega is part of this, let's say, network of 4 tools which are freely available for in-silico mode QSAR and also read across. And from, I refer in particular to Vega, the Danish QSAR database, Ambit, and OChem. And from this link, from this project, Concept Reach, you have access to large, many hundreds of models, and you can choose, for instance, for the reach endpoints, if you are interested in Phys-Chem, in ecotoxicity, in toxicity, or so, for models and read across. And so you have the collection of the models in this network with some pieces of information regarding the chemicals and some statistics about the models. And also from the same, from the sources learning, you have this, which I think is quite useful. For instance, this ebook of 160 pages where you have a full detail on how to use and how to interpret the results of Vega, the models, and read across, and how to combine the information from ToxRaser, Vega, Vera, and so on. And there are also tutorials and videos if you are interested for the different tools. Janos is a project funded by the German UBA. These are the partners, Mario Negri, Code, and Knowledge Miner. And it is dedicated to PBT, CMR, and endocrine disruptors. So the German UBA is interested in prioritization, and so they wanted the software for these properties according to regulatory schemes for the parental compound and for the degradation products. So simultaneously, using Janos, you run about 50 different models to prioritize the pollutants in Germany, let's say. And so it is based on the individual evaluation for PBT, for instance, for persistence and so on. And then if you have in the database, or if you want to use your own experimental value, this is possible. And for the experimental value, if you have multiple values, and for the predicted value, again, if you have one or multiple, the reliability and the concordance is evaluated. There are other checks, for example, related to the solubility, water solubility, which may be useful to double check how realistic is fish toxicity values, for instance. And overall, at the end, all these elements are integrated. So there are many complex schemes, for instance, for aquatic toxicity, according to the regulation. This is very important to evaluate toxicity. According to regulation, you have to provide information for chronic, for the 3 chronic toxicity, for the 3 levels, algae, daphne, and fish. And so there are multiple models for each of these endpoints. Some are categorical model, other continuous, and so they are integrated. But then the system also takes into account information regarding acute toxicity and acute to chronic ratio, and as I said, for instance, information regarding solubility. So overall, this is combined into one single value, but the system is transparent. So if you are interested to see the toxicity for fish or daphne, this is possible to visualize, of course. And so at the end, you can get PBT or CMR or very persistent, very cumulative, and so on. And basically, the output, you have a sum. In this case, the software runs collection of substances, so it's for prioritization, not one, but 1,000. And so you have a summary for instance, the first chemical, and you have evaluation. If you can select if you are interested only in PBT or only in CMR or whatever. And the software provides an overall comparison label indicating, okay, maybe you have issue for reprotoxicity, and the information regarding persistence for PBT as a value ranging from 0 to 1, with information regarding the uncertainty, the reliability of each assessment for persistence, for bioaccumulation. And so these 2 elements, the assessment and the reliability, are combined into one score. And the system works on the parental compound plus degradation products. So automatically generates what you may expect to occur into the environment, because there are 235 degradation pathway occurring into the environment. So the system runs also for this. Okay, this was an overview. If you have questions regarding this first part.
Thank you, Emilio. Indeed, impressive to see how many projects, and good to see that there is material also to follow up on, like the details that, of course, we cannot get today. I want to reassure participants that we got the slides from Emilio, so no need to take note of all the links, because you will have the slides. If there are questions, I would recommend people to raise their hand, so we can follow. And while people think about their questions, I took down a few notes, Emilio, and maybe we can go through those. For ToxRaser, I've seen that there is the possibility to select the endpoint of interest to identify the analogs. And my question is the selection of the endpoint because you have a different type of chemicals with available with data, or is because the similarity is defined differently depending on the endpoint? This is one question.
Now, the similarity is measured using the Vega similarity tool. So it's always the same, but you have to select the endpoint because indeed, as you said, there are the experimental data for fish toxicity or for mutagenicity. This is one part of the story. The other part of the story is that depending on the endpoint, there are elements for reasoning. So if we are interested in bioaccumulation in BCF, you will have the software will identify not only the most similar, but the presence of certain moieties or certain fiscal properties which are relevant for BCF. But in the case of mutagenicity, you will have other elements which are relevant for mutagenicity. So for instance, epoxide is very relevant for mutagenicity, so this is clearly indicated, but I'm pretty sure that the presence of an epoxide is not notified, is not used when you want to explore similar compounds for BCF, because we mainly relate to more general global features.
Okay, so in a way, when one combines the similarity, the Vega similarity, which is endpoint specific, with the reasoning, then the analogs are tailored for the endpoint. Now, irrespective of the fact that data could be available for different substances. Okay, then I had one question concerning the projects you have on cosmetics, where you mentioned, or I've seen on the slides, in some case adsorption, and my question is, do you predict any of the toxicokinetic or ADME properties, or where do they come from? Is something you have in the guidance?
Yeah. I'm so sorry, I lost you the connection. So if you can repeat your question regarding the cosmetics.
Okay, good. Good that you are back. We could see the slides, but you disappeared indeed.
Yeah,
In cosmetics, I've seen in some slides a reference, for example, to absorption, and I had a more general question on toxicokinetic. If you predict any of these properties, or do they come from guidance, or how do you take this into account?
So the system regarding the skin penetration takes into account three values. One possibility is that depending on the exposure route, the system provides the official value. So for instance, for the skin, skin penetration, the default value, in case you have no information, is 50%. For oral exposure is 100%, and so this is provided. But in addition, the software also runs this model for the skin penetration, and it also provides information if the penetration is in high, say, level or low level. So you have there's a possibility that the penetration is higher than 50%, and so this is reported, or less than 50%, and so this again is reported. And so based on this, you have the value margin of safety, which are calculated using the default value, so for instance 50%, or if it is 80%, you have a higher amount, which is relevant for the systemic toxicity, or it may be lower value. So this again is reflected in the calculation of the muscle. But all the different scenarios are provided, so that the user is informed that there's official value plus some refined value using the skin penetration information.
Okay, thank you, clear. I have a last question about Janus or Janus. I understood that the degradation products, which are also predicted, like the properties of the degradation products are predicted, they are predicted from the parent because of a library of 235 pathways. And I was curious to know like where this library of pathways come from. And also a second question on Janus is about its availability, because if I'm correct, it's not as Vega.
No, the software you can download, sorry, regarding the last question, you can download Janos and you can run. And if you're interested, we can also send you the report. It's, I think, 100 pages explaining everything. We are in a process of publishing the paper, and so the software, so the documentation paper will be available also in this way, but the full extended documentation, if you are interested, I can send you. Regarding the pathway, they originate from the work done by the Minneapolis University. Then that guy retired, but this was implemented by the Zurich Center and Catherine Fenton in particular implemented. Within Premier, we are further extending this pathway. So maybe I will say something more in the next slides.
Okay. I think we are familiar with that library of reactions. I think in the past we have heard that in the very beginning they were implemented with a little bit old technology, and it was difficult to have them in modern software, but probably you or someone else has done the work.
They are implemented as SMIRCs because they are reactions.
Okay, thanks. And okay, you said we'll see also something later. I see a question in the chat from Tatiana Netseva, and she asks if Janos could be updated also with science for mobility. And the background to this is that now, as much as we identify PBTs and VPVBs, we also identify PMTs and VPVM substances. Did you get any request from UBA to update this, or is there any plan?
Yeah. Indeed, I will come about that in the next slide in the future project. So I can reply to this indeed maybe slides.
Okay.
So here I refer indeed on what's next. And so which are the projects? This is the main projects which are ongoing and now are listed here. Project from, let's say, public body, the European Commission or EFSA. And so, for instance, Softera, it is funded by EFSA. It is, so Eduardo knows very well because he's responsible for this on EFSA part. And it is related to the further development of open food tox database. The partners are Mario Negri, Molecular Network, Altamira, and SIN, and it relates to the migration of Open Food Talks version 2 into Euclid, increasing the system and also developing 20 new models, in silico model based on the Open Food Talks database. Not only silico model, but also read across and grouping. And here there are mixture of many endpoints, quite interesting, for instance, not so commonly addressed, but of interest for EFSA, for terrestrial toxicity. So speaking about Collembola, licking fly, the quail, but also amphibians, and benchmark those. We're thinking to exploit open food talks, and also fill data gaps, maybe with prediction, and this is, of course, a project to support the EFSA unit. For instance, regarding the grouping of interest, maybe the grouping related to flavoring, to botanicals, to pesticides, And indeed, the grouping this for the categories, for the sector, but also the perspectives may be different because as defined by the different units, in some cases, this grouping is defined according to structural features, or maybe in the case of pesticides, according to mode of action. So tools to address the mode of action of pesticides are quite important for EFSA, of course. ADMET for NGRA, New Generation Risk Assessment, is another project funded by EFSA. We are partner in this case. The project is coordinated by Fraunhofer, and this is related to the toxicokinetic, the microbiome, many in vivo, not so much in vitro studies, surely, and also a little bit of the in-silico part. And indeed, also here we have to develop, and we're developing 15 new modes separate in addition to the other 20 new modes, but in this case, more related to the toxicokinetic part. PARC is a huge project. I'm pretty sure that you know very well better than me. Mario Negri is involved in work package 4, 5, 6, 8, and 9. And so that a lot of activities within PARC for us, for developing new model for non-genotoxic carcinogens, or for, again, for risk assessment. In particular, we are involved in work package 8 for the topic where we're speaking now. So we are, let's say, working to integrate the Vega models into MCRA for the exposure and for risk assessment, and also integrating Vega into the Integra software for risk assessment, using Vega for safe and sustainable design, so relating again to ToxRaser. And indeed, UBA is quite interested in further development of Janos. So mobility surely will be addressed here, because this is, as it has been suggested, absolutely a new property to be considered. But also here in Premier, we have a specific project to introduce mobility. Premier is a project funded by the European Commission and the pharma industry. Indeed, the topic is to evaluate the ecotoxicity of pharmaceuticals. We are responsible for the DAS and for the development of in-silico models and read-across tools. The DAS is the database of a pharmaceutical, with FISCAM, environmental, ecotox, environmental risk assessment. So the collection of all the data with quality control, with information from the authorities. And indeed, the idea, and we are in close touch with EMA, because the idea is to donate the DAS to EMA. Every month we have a meeting with them for, let's say, conceptual scheme, but also for the practical implementation part in order to be fully aligned. So here we're speaking about model for ecotoxicity and read across for drugs, but also the mobility and also new degradation pathways, because Catherine is also partner of this, and so she's developing a new pathways for the environmental degradation, and we will implement them again. Vera is a software which is developed within a number of projects, but also in this case, regarding Premier, this project is a software for read-across, and we are studying read-across using classical substances, not pharma, and pharma data. And indeed, if we make a read across with industrial chemicals, let's say, and if we use data evaluation with good reliability, we have an R squared, let's call it this way, maybe it's not the right term, of 0.6, but if we are referring to pharma, the R squared is about 0.8 for part of the chemicals, when the system indicates that the reliability is high or moderate. If the reliability is low, which occurs for let's say, maybe 60% of the chemicals, R squared is lower, so we still have to work. On Tox is another project which is related to organ-specific toxicity and specific pathways. So for instance, for DNT, liver, kidney, and not everything, but for liver-only steatosis and cholestasis. So we're speaking about AOP, and in addition, AI tools. And Mario Negri is mainly involved in the development of models and the read across of the chemical domain. So for the development of models for AOP in particular, we are investigating models for the molecular initiative events, for this, for instance, the molecular initiative event for steatosis or for cholestasis, and these are the state of the art where we are, if the model is already sufficiently good, or if we still have to work. This is QSAR, but also we are developing tools for read across, so trying to identify structural alerts using SARPI. And these are the statistics in terms of for each, these are the different molecular initiative events, the statistics in terms of specificity, sensitivity, and balance and accuracy. If it is in gray, we have not enough data, but basically if we have 10 chemicals, it's difficult. We have seen also previously, both to develop model, but also to develop read across, obviously. We have a project related to endocrine disruption, 2 projects, Oberon, funded by the EC, coordinated by Paris Descartes, Endocrine, funded by ANSES, coordinated by INERIS. The French coordinators is not by chance, because, as you know, France is very, very much active on endocrine disruption. And so we are developing models for its estrogen, androgen, thyroid, and steroidogenesis, and nuclear receptors. Alternatives is a project funded by the EC, coordinated by Politecnico Torino, dealing with mixture risk assessment, particularly related to cardiotoxicity, and so we are developing a model for mitochondrial dysfunction, oxidative stress, and cardiotoxicity, of course. On foods, you know, in Europe we have a Green Deal. In Italy it is called PNRR, and this project funded by the Italian PNRR, so it's the European Green Deal. It's dealing with nutrients, effect on nutrients and frailty, old people, pregnant, so how the food ingredient may be beneficial or also with some adverse effects. And so here, for again, we are addressing oxidative stress, but also protective agents. So we've seen in-silico model for toxicity, but we have also seen a model for exposure, so for risk assessment. Here, we have a different framework, so not only adverse, but also beneficial properties. So this is somehow a different perspective, quite interesting to me. And then we have a new process, so just started a month ago. So I simply mentioned that this is a project funded by the EC. The coordinator is from Portugal, dealing with the use of quantum chemistry for toxicity, in particular interested in liver toxicity and mechanism. AI chemist is Marie Curie project for training coordinated by Igor Tetko. It is about the use of AI chemistry, particularly we are addressing organ-specific toxicity. And a new project we just started is Polynera, funded by the EC. Coordinator is Aarhus University in Denmark, addressing pollinators different from bees. And so the development of in-silico model and read across for this kind of endpoint. So, quick overview on what's going on. If there are questions.
Thanks, Emilio. Again, I'm looking at the participant list online, and I see that Juan raised his hand. So please, Juan.
Thanks a lot, Emilio, for this presentation, because indeed every time I attend a webinar by you, I'm learning more things, and I'm really impressive of all the work that you are doing on this area. Regarding the OnTox project on which you are participating and you are developing structural alerts using SARPI for target organ toxicity, it is planned, because I have seen that indeed under OnTox there are also some companies there, and I don't know whether the results of this project will be published, or whether you are planning, for example, to publish and to make publicly available, for example, the list of structural alerts for target organ toxicity. Thank you.
So thank you for the question. So all the models that we will develop within OnTox and all the other projects will be implemented in Vega Hub. In addition, in the case of OnTox, this will be implemented also in what is called OnTox Hub, where there will be not only our model from Mario Negri, but also, for instance, model from the work package dealing with toxicokinetic, so PKSIM and other tools. So there will be a molecular network. Also, they will develop models. So OnTox Hub, through OnTox Hub, this kind of model will be also available. And in addition, there's also Thomas Hartung, who is working with RASER. So we will provide this kind of structural alert and chemical description and so on. And I think that also within RASER, these pieces of information will be publicly available. So there will be at least the 2 or 3 separate freely available tools to get this piece of information.
Okay, thank you.
Checking if there are more hands up or in the room. Looks okay. I have, Emilio, one comment and one question. One is on the DAS database for pharmaceuticals. In the beginning, I thought that is a database from EMA, but then I heard that you want, or you could donate DAS too.
Yeah. No, indeed, it is, well, they have their own database, but this is mainly, let's say, it's a repository of opinions, so it's not so much structured. You don't have to think about the database as in the case of Open Food Talks with the table of the chemical. It's a repository, so they have chemical A, B, C, pharma A, B, C, and progressively the opinions on this pharma, if it is toxic, on the effects and so on. The DAS is a database with information generated according to GLP from pharma industry, but also taken from other sources. So most of the data are with a very high quality. double-checked and curated with full details about the temperature, the pH, the number of animals, the duration, so that everybody can double check. So they're very much detailed in this. For the FISCAM, for the ecotoxicity, but also the therapeutical classification. So not for the human tox, because this is only for ecotox, and the environmental properties, of course, BCF and so on, and persistence.
Okay, no, yes, my comment was that when this database is ready, if you are in the position to donate it to QSAR Toolbox, please consider that too, because then the database will become available to...
Absolutely, glad, I will keep in mind, but I think it was already anticipated that this will be offered, of course, to EMA, but also to other, by the way, there may be also therapeutical, veterinary pharma, so maybe also EFSA has some interest.
Okay, very good. And maybe in the interest of time, we can also move to the third part.
Yeah. So
yes,
the last part is dealing with read across some considerations. The topic is quite difficult because there are some issues. How to, if I read across, we need a similar compounds, so somehow we have to select. My first initial issue is to be sure that we do not lose in our initial steps some important similar compounds. We have to define the threshold, so this is an issue because the threshold is a continuum value. We may have similar compounds with conflicting data. A criticism, there are papers related to read across indicating that this is not so reproducible for the role of experts who may have the different opinion. And another point is that usually this is done one by one, so it is difficult to it's not the perspective of QSAR, there we have 100, 1,000 chemicals, so we can play with statistics. Similarity on a mathematical point of view is not transitive. It is reflexive on a mathematical, it's not transitive. So you see this black rectangle and then something light or on the other side, something darker than darker. So we can say that from the left of the second is similar to the first and the third and so on. But if we proceed in this way, we arrive to conclude that black is similar to white. Of course, this is not possible. So we have to identify threshold. So this is the difficulty and the fact that a similarity on a mathematical point of view is not transitive. Another point that we are assuming that this function of similarity is linear. Maybe not. I don't know if you have driving the car, if you have this experience driving a car in San Francisco, at a certain point, you realize that something strange is happening and the street is not flat, but going uphill very sharply. And so when is it possible to identify this? Is it possible? Is the similarity, is it linear or not? Do we know this? And similarity, we have different metrics. So we can use a chemical structure, FISCAM, toxicity information, structure, toxicokinetic, experimental values from omics, and so on. But which is the relevance for our specific endpoint? So are they at the same level so that we can use a kind of parliament approach with same vote for each or not? Probably not. And are we sure that they are orthogonal or independent? Probably not. So what do I know? Kesage, Montaigne, this is the philosopher, but very, very modern, I think. He was saying Kesage. What I know, in the case of Rita Cross, I surely know the chemical structure, so I'm interested in this target chemical. Maybe I know the toxicity pathway applicable to the target substance. Maybe I can imagine that the PhysChem, that the toxicokinetic, that other features are important. Maybe yes, maybe not. So Vera tried to cope with all these difficulties. And the first point is how to gather similar compounds. So in order to be sure that we do not lose. So the first process is gathering and then pruning. For gathering, we have two approaches. One is structural similarity with Vega 065, which is very low, so in practice, except in everything for Vega, usually we have 0.985. Or another strategy is using multiple metrics. This is what we call Vera entities. So to apply many steps, and this is absolutely unsupervised, independent from the endpoint, using in the current version 10 different perspectives, so from the reactivity to metabolism to PhysChem, degradation, and each of this space is split in 3 parts, and I project my target compound into this reactive space, and so my target compound belongs to this subspace for the reactivity, but for the steric part to this other part, and so on. And so in practice, I can then search and identify all the similar chemicals which are, let's say, identical. So they if I use a vector to identify these 10 spaces, the vector for the first component will be 001 on 100. So I can identify all the chemicals which are similar to the target that they are exactly in the same subspace for the 10 features. So I don't use threshold values, I use membership. At this point, I can start playing with the pruning. So which, once I have gathered the similar compounds, which are the relevant for me. If I have information regarding the mechanism, I can use a supervised method, so I can guess metabolism, or toxicities, something related to that, and so I can use this, or I can use the 10 metrics, and so this explore many different possibilities. In the supervised version, I am using information regarding structural similarity, as I said, the presence of structural alert plus a grouping for similarity. So I can search for all chemicals with structural alert number 1 and then 2 and so on. And in addition, all the chemicals which contain the structural alert plus the molecular group, the chemical molecular group 1, 2, 3. And so they share in common the same feature. So I'm working with clusters of similar chemicals. So I gain membership and not the similarity. And I have multiple multiple chemicals within a cluster. And so maybe the first cluster is mainly inactive compounds, and then the second and the third is mainly with active compounds. So I can deal with mathematical tools to arrange this. In the case I do not have information regarding the toxicity, what kind of toxic I can expect. So I use the information regarding the entities, and I assign a weight, for instance, in the case of, I think this is for, I remember, fish toxicity, let's assume, And I've seen that the feature which is more important is reactivity, the feature which is less important is the FISCAM, for instance. And so I assign a weight to each of these features. I look and I extract the three most similar compounds with this feature, the three most similar compounds with this feature, and so on. And I combine the information and the similar compounds using the weight. So as a summary, I have two possibilities, and I can combine if I have information regarding the structure alert or regarding the similarity unsupervised, let's say, and I can combine, so I can get, in case, let's say, of fish toxicity, I can combine and make the overall assessment. The software also provides the presence of structure alerts with the prevalence of toxic or non-toxic compound with a certain structure alert, but molecular groups with a prevalence of toxic and non-toxic compound with a certain structure alert. Sorry, no, these are my molecular groups. And then it provides the indication where is the target compound in the 10 subspace and the role of the different subspaces. And so for each of the subspace of the 10 subspaces, the software provides the most similar compounds for considering the steric hindrance or metabolism. In the case of metabolism, the software also provides the pathways of the degradation. I can have hydrolysis or oxidation and so on. And so at this point, I can, the software provides information regarding the most similar compounds combining the entities or the most similar compounds considering, for instance, the structural alert. And so the user has these two kind of elements. In the case of a structural alert, in the case of molecular groups, that these are indicated, and so this can be also used for reasoning to better evaluate what the fragment is highlighted, to better evaluate the role of this piece of information. We have one first paper regarding carcinogenicity, able to correctly predict 70% of the substances. For fish acute tox, as we have seen, we have with higher reliability 80% of let's say correct. So this is the last slide, and this way we are trying to avoid losing important chemicals. So pruning is very important, so that we pay attention not to lose them. We use multiple metrics and not only one. We use membership and not a threshold. We compare clusters and so this also helps us to better cope with the issue of individual conflicting values. The software simply requires the structure, so we do not require experimental values. It provides a measurement regarding the reliability and the applicability domain of the tool. It integrates two approaches. It is modular, flexible, so we are adding other features. It can work in batch mode if you have 1,000 subjects. And so in this way, we can refine the software because we can learn and improve the evaluation. This was the overview of what we're doing regarding read-across for Vera software. If you have questions.
Thank you once more, Emilio, for also the presentation of this part. I look again at the participant list and in the room. And maybe, okay, I see Doris, hands up.
Maybe more a comment. I mean, thank you, Emilio, for the presentation. Really, really great. I'm thinking now because we just had the presentation on the QSAR assessment framework, and one element that becomes more and more important is the similarity check for chemicals in the dataset. I was wondering whether we could utilize Vega for a harmonized check of similarity, and I would be interested in your opinion on that.
Yeah, sure. Maybe I can also stop sharing. Yes, surely. Vera is freely available. It's also available from GitHub, so everybody can download. But I can surely we can discuss, and if you want to know more and explore how you can maybe utilize in this way, you can. We can surely try to see if there may be something useful for you. So the software is freely available, so we can provide it to you. It works in Python, or we can think about other possibilities through a Docker if you are interested, in particular in the software. If you are interested in more on the conceptual schema, this is also a possibility. So we can gladly talk about that.
Okay, no, indeed, a good point. I think looking for similar compounds is always a question that we get. How do I look for them? How does ECHA look at it, and how can we make sure we see the same? And I mean, of course, tools help standardization. I had just one, perhaps a small clarification, but I didn't understand from the slides. When talking about these different entities, there were 3 colors in the plot, and I didn't understand what are these colors.
Yeah, indeed. So we have a database. Was maybe surely too fast. Just an overview. So we have a database of structures, only structure, no properties. And so let's imagine, I don't know, fish chem. The fish chem, what we have seen, the fish chem actually is composed, but not only one property, but you have log P, solubility, blah, blah, vapor pressure. And so we combine this multiple fish chem properties into one metric. At this point, this is simply a chemometric representation of the space, and it is split in 3 part of high, medium, and the low values, let's say. And this is calculated because we have a database of 10,000 substances. And so we can calculate, I don't know, let's imagine one single property, I don't know, water solubility. So if we have only one dimension. And so let's imagine high, low, moderate water solubility in one dimension. And my target chemical will be, will fall in the range of, I don't know, high solubility, because there are other similar compounds with high solubility. So this, in this case, I use only one dimension of solubility. If I use solubility, vapor pressure, so this is a multiple space, and I allocate my chemical because I don't know the property. What is used is the database of these 10,000 chemicals, and so I look at the similar chemicals similar to my target compound if they have solubility which is high, low, or moderate. So this is simply cutting in 3 parts the domain of solubility or the multiple space.
Okay, yes, I think I understand. The other question that I have is on the fact that we have seen in a couple of tools the fact that the degradation products are predicted. Do I understand correctly that like you don't have a separate model application like in Vega where I can just see the degradation products predicted by the tool, but I have to use one of the other tools that include this calculation to look at the degradation products predicted.
Oh no, if we were speaking about metabolism and if we are speaking about degradation products, the process, the metabolizer, these are also reported, indicated by the software. So there was this slide.
Yeah, what I meant is that I cannot just input a structure in Vega, for example, and look at the degradation products. I have to, for example, use Vera, and this is a part of its report. Or
okay. No, I see. Also, now I see your point. No, indeed, we are thinking also to make available the individual tools as a separate component. So if someone is interested in this, so within Premiere, we are aiming to have to that, so a kind of implementation so that you can simply run this. Or similarly, in the case we have a model, for instance, already now in Vega for steatosis, which runs maybe 10 separate models for the molecular initiative event, but it does not provide, so you may be interested, I don't know, only in PPR gamma. But you have the steatosis model where the model on PPR gamma is used. So indeed, this is a good suggestion, and we are working to implement the individual submodels, which in many cases are inserted into this, let's say, more composite model. So this is a good suggestion. And the same applies also to Janos. Within Janos, we have some models present in Janos, but not available as individual model.
Okay, yes, I was asking in particular about degradation products because that's something that many stakeholders, including ECHA, are interested in. In the public space, there is not very much, or one must know where the tools are, and I think Vega has a good visibility, so people would be like, it would be easy to find for some people if it's there, and it could probably be useful. Okay, I have no more questions in the room. Everything has understood all of it, and no questions in the chat. So Emilio, I would like to thank you once more for your availability and this like a huge presentation. We have like a lot of food for thoughts, and thank you also for being available in case we have specific questions as follow-up when we look at the material. I will distribute your presentation to the participants, and yes, I think here is lunchtime now. Everyone is happy to go. Thanks again, Emilio. Thank you to the online participants.
Thank you, and maybe I'll stay in touch with Doris if we want to better see how to collaborate for read across. Okay.
Thank you.